Yes, okay. So when I finished my PhD, actually I was working in Tilburg University, and around this time this new book of Gelman and others on Bayesian data analysis came out in '95. So we were at this time reading this book on Bayesian data analysis at one side, and on the other side we were involved in the first test construction for our national assessment on reading comprehension in Flanders for primary school kids. And actually those two things converged in the first random item effect model, because in the reading assessment scale we actually had different educational standards, and we wanted to not only to talk about the items but also to say something about the educational standards. And so we were looking for a model where we could model item groupings, so have the items at the bottom, and the hierarchy on the items consists of grouping the items according to their educational standard. The example actually is explained in the book also on page 193, but it's not necessary to look it up. So we had the Bayesian influence and we had the influence from practice, and this converged in this first model on random item effects, the first hierarchical IRT model at the item site. So this is how we started this line of research. And so at first we developed the model for item group predictors, but of course then we saw that the LLTM can be seen as a special case. And then we had the model with item predictors developed. So this is the kind of history behind the chapter. Well, okay, 1B is how did writing this chapter influence your future research agenda? Well, actually it was not for me the influence of writing this chapter in particular, but being involved in the book from a theoretical point of view and from a practical point of view. From a theoretical point of view, actually working on the book made us think statistically in psychometrics. Beforehand, we were thinking of a model and we had to estimate parameters, parameters for items, parameters for persons. Now we are more and more thinking in, we have data and we want to look which predictors can be used. And actually there's an equivalence between estimating parameters and estimating the effect of predictors, but it's a different way of thinking, and actually I think this has influenced us from a theoretical point of view. Not to think in terms of the classical way we were looking at IRT models, a set of parameters and estimating them, but thinking of these are data and which are the predictors at the item side, at the person side. And then from a practical point of view, I think the influence was that now we have seen that for estimating all kinds of models, we just can use programs like SAS or whatever, so that we don't have to wait for a particular program to come out to estimate an IRT model. Although I have to admit I still use the old programs, because in these old programs like Conquest and OPLM, we still have the implementation of how well do the data fit. We have a lot of fit statistics, and this is not really programmed yet, I think, in the statistical packages. So that was 1B. Yeah. Okay. Okay. Well, yeah. Actually, I might be a little an exception, because I was trained as a psychologist. Now I'm most of the time working for the Department of Education. So I am already influenced by both sides. And then, yeah, it's good to be part of a broader scientific community, and so it was nice to work together with people from your university as well. Well, I think it's for the measurement community because it's not really complicated statistics, I think, for the statistical community. But well, I think it can be used in educational measurement. With respect to the other questions you have on 2B and 2C, well, for me it's what do you have to know, or what is a way of getting good mastery of these topics? I think the book is a good way. I mean, both setting which type of statistics you need to master, and I think it's explained well as well. So. Yeah, yeah. Yeah, well, I mean, it's already written in the book which kind of prerequisites you need. I personally, I'm also not trained as a statistician, and I've experienced also difficulties sometimes in how far do you have to grasp all those technical stuff. But most of the time, it's rewarding to study. Although you have, it's very handy if you have somebody next to your office who you can ask, is this important or not? Or it's good to have somebody who masters it, where you can ask questions. Okay. Well, this this quote comes from the fact in the introduction where I wanted to show that although it's very uncommon to have random item variation in item response modeling, there still are already some places where you find it. And the example comes from the Bayesian estimation of standard item response models. And in Bayesian estimation, you always have to assume not only your model, but also what you think about the parameters beforehand. And that's why I added this little quote on the handout. So I just have rewritten the formula for a Bayesian approach there. So what I've written there is also in the book. It's that the posterior distribution of a certain parameter theta, given the data y, is proportional. This posterior distribution is proportional to the model. So the g of the function of y given theta is the likelihood. What is the probability of a particular observation given the parameters of the model? And what is also added in a Bayesian approach is what do you think beforehand about the parameter? This is the prior distribution and it's denoted as g theta. So the idea of a prior distribution is coming from the fact that in Bayesian statistics you are not thinking of parameters as having fixed values, but you think of parameters as being random variables, as something about which you are unsure, but you have some knowledge where the parameter will be. So the prior distribution gives you an indication where the parameters are. Yeah? Well, you can give this a substantive interpretation, but you can also just use this as a technical way of estimating data, the Bayesian approach. And in a technical way, you just say, well, I have my likelihood, and I need to give some information about where are my parameters. And this is what is done in the Bayesian estimation of the Rush model. That is, we have the Rush model, so the likelihood is the Rush model, but we also have to say something about the item parameters, about item difficulty, and about the personability parameters. For instance, we can add the assumption in the prior distribution that the persons all come from a standard normal distribution or a normal distribution. So we give some knowledge about the parameters, but it can be vague. But we have to add this knowledge in order to be able to estimate our model in a Bayesian way. What I do in the quote on this chapter 189 is to give a more substantive interpretation to this prior distribution. Because I say, well, you can see, you assume that, for instance, that the items come from a particular prior distribution, but you can see, take this as, you can interpret this in a substantive way by saying that all items come from one item population, but we see that the items are without a design. That is, we just say they all measure a certain ability, or and they are homogeneous in this respect. And we just add these items to measure this latent dimension. So it's a substantive interpretation, but just given to something which is needed to estimate a model in a technical thing you need for estimating the model in a Bayesian way. So it's yes and no. I am referring to the unidimensional assumption, but no, because you can have a Rush model without this assumption. So you can have just say, well, I have a set of items. I want to estimate whether these items of these tests constitute latent dimension. How are these items related on this dimension with respect to difficulty? But I can also add a prior assumption that these items are coming from a single distribution. So this is, of course, not very interesting way from a substantive point of view, but it becomes interesting if you then have different kinds of populations of items. If you have different item groups, then you have your set of items, but then you model the different groups of items and you can compare the difficulty of the item groups. Oh, it is. It can be. In the example we give with respect to reading comprehension, it's, I think, on 193, page 193. We have a test on reading comprehension, but so we have different texts and several sets of items for each text, but we have grouped the items according to the curriculum standard they measure. For instance, we have a set of items corresponding to some text that from the curriculum standard require a descriptive level of processing only, and they go about, I don't know, school texts. The school text will probably be on a structural level with respect to the level of processing. Or we have advertisements that the children have to be able to evaluate. But we assume, and actually the data showed us, that all those different texts and the items, we're measuring a single dimension, reading comprehension, but we still were able to tell something about the difficulty of the different educational standards. Actually, for the children it turned out that evaluating advertisements was the easiest. So they were these were items that on the average were easier than the other items in the tests. And I'm not sure about the particular example, but I can imagine that structuring a school text was one of the more difficult item groups. So we have one dimension, but different distributions of items on this dimension. Yeah, actually you can compare it at the person side with what was in the previous chapter. There you have also, all students have a common ability level, but you can distinguish between girls and boys, and so on this common latent scale you distinguish different distributions of person ability. Yeah, and so we think girls and boys do have the same latent ability, but they differ with respect to their distribution. On the average, there are differences, or maybe in the spread of ability on the scale, there might also be differences between the two groups. So it's the same kind of idea at the person side as at the item side. Okay. Yeah. Well, maybe we can look at page 9 to table 1.1. It's the example of the verbal aggression data. So page 9, table 1.1. Page 9. It's just one of the examples I also show. I also applied the model on the verbal aggression data. So in this case, we have the 24 items. Bus fails to stop for me. I would want to curse is one item. And what we do in the linear logistic test model is we are not going to estimate each item difficulty separately, but we want to look at three kinds of predictors for the items. So we have the two predictors, is it a want item or a do item with respect to the behavior mode. We have two kinds of situations, is it another to blame situation or a self to blame situation, and three kinds of behaviors. In this case we have 12 different levels of item groups, 12 different levels because we have 2 by 2 by 3 different predictors and we have an orthogonal design. And we would like to know if we only use these k equals 12 item predictors, how well can we measure all differences in difficulty for the 24 items. So indeed it's the case that we group the items according to a set of criteria. We give some item predictors or we give some item groups, and we then want to look in the LLTM or in the random version of it that is described in the book, how well can we describe all differences in difficulty if we only use those three item predictors, those three different kinds of characteristics of the items. It's again, it's like a regression model, or it's like what Wim told us before last week. There we had personability, and we wanted to look how well can we predict personability from what we know about socioeconomic status, about the school, about the district where the school is, about the age of the child or whatever. So we have a set of predictors and we want to look how well can we recover the real ability, how well, in this case for the item side, how well can we recover the real differences among the items. Yeah, yeah. Yeah, yeah. And so actually what you can do with this model is in a sense test the theory about your items, test the theory about item difficulty. If we would know what the determinants are of difficulty, then we know more about the items than if we just have scaled them on one latent dimension. We know more. Mm-hmm. 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 Well, I'm not so I'm not an expert in generalizability theory, but I think indeed it's the case that in generalizability theory you assume that the items are a sample from a certain universe, just as the persons taking the test are a sample from a universe, and the raters who rate the items are a sample from a certain universe. I think what is new is that we now also add the fact that we look at combination of item characteristics, and that for even this more specific set of items we have a population. So we have a population defined, not just a general population for all the items, but it can be very specific. Actually it's on equation 6.2 is like the random sampling interpretation of the model. And the random sampling interpretation indeed says that for a particular item we assume that it comes from a certain distribution, and this distribution is characterized by a mean difficulty beta prime and a certain within group variation of the items. It's in a sense it's related to the fact that if you look at 6.1, where we have another version of the same model, maybe it's related to a facet design on the items. That's something that is also related to the field of generalizability theory, and where you also have a kind of design about the items when you construct your test. You have a facets design. I don't know. Yeah. 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 Although I do like the idea of the generalizability theory, and if you look on page 193, if you assume there is just one group of items, so G is equal to 1, then this formula that is on page 193 is like calculating a domain score. So you refer to the universe of items as the domain you want to measure, and then with using this model you can now calculate the probability of success not only on one specific item from the domain, but on the population parameter itself. And so you kind of have a domain score for a person. After taking the test, you're not saying you are this level of ability, but you immediately say, well, your domain score equals 0.8, which means you master the domain very well. And when you say such a statement, you're referring to a population just as in the generalizability theory you do. Mm-hmm. Yeah, actually on page 193 there are two examples of this idea of item cloning or on considering the items to be a random effect. One was the example we just discussed about domain scores. The other example is the Glas and van der Linde paper, where they refer to the area of automated item generation. I have a little example on the handout at the bottom page. For instance, suppose I would make a mathematics test for children at the end of primary education on whether